Welcome back to our continued discussion of rotation. Last time, after having reviewed rotational kinematics, we had a discussion about rotational inertia as an important quantity that's going to help us understand what causes rotation or impedes rotation. And we talked about the fact that rotational inertia, also known as moment of inertia, has to do with not only the mass of an object or system of particles, but also the distribution of that mass or the distribution of those objects in your system about a rotational axis. We quantified this further through the following equation, and we did an example where we computed the moment of inertia of an example problem. And then I also said that if you are looking at an extended object, this sum would turn into an integral, something like this, where you consider a little infinitesimal amount of mass and its distance from the rotational axis, and you integrate that throughout the entire extended body. But generally, I said last time that you can often look up the results of this integration on a table which will tell you what the rotational axes will be for different types of objects about different axes. And then I left you with a challenge to go ahead and try and flip your phone in multiple different directions and see which axis was the most difficult to flip your phone about. Through experimentation, you may have decided that ultimately it was this bottom example here that was the most difficult to flip your phone about that axis. So the question then becomes, well, why is that? So I mentioned a jargon last time, the mid-axis theorem. And this says that counterintuitively, it's not just which axis has the greatest rotational inertia that tells you something about how difficult or hard it is to flip it. It has to do with how that moment of inertia compares to other moments of inertia about the same object. So, for example, let's take our phone and let's model it as a rectangular prism, and the different axes of rotation that we discussed are X, Y, and Z here. So X would result in what we ultimately concluded was the most difficult, or hopefully you concluded was the most difficult to rotate your phone about, flipping it that way. Y, you're flipping it around this way, and Z, you're flipping it around this way. Okay, now the equations that you see here tell you for a slab what the moments of inertia are based upon these parameters A, B, and C that are the length, the height, and the width of the phone. So you can conclude without actually putting in the numbers, just based upon the proportionalities here, you can conclude which of these is going to be the greatest, because you can clearly see that A is greatest, and then C, and then B in terms of the dimensions here, here, and here. So what that means is that for axis Z, rotation about axis Z, where we include B and C, we're including the smallest two. So this is going to be the smallest of the three moments of inertia. On the other hand, axis Y includes the two largest, A and C, right? Okay, those are the two largest, so that's going to have to give us the largest moment of inertia. This intermediate axis or mid-axis is in the middle. This is intermediate. And as such, it's going to end up being the hardest to rotate. The explanation here is that any perturbation off of this will actually it's an unstable rotation that will the object will try to get about this axis or this axis instead. Okay, so that's an interesting little theorem. Another theorem that I want to introduce is something called the parallel axis theorem, which allows us to compute the moment of inertia of an object if we want to rotate about a different axis, but one which is parallel to one through its center of mass. So for example, here we have some sort of disk or sphere, and this is the moment of inertia about the center of the mass. And so if I instead want to rotate it about this axis here, I just need to add on what the md squared is, the mass times the distance squared over to that axis. Okay, but for most objects we can, as I said before, refer to this chart, and we can find then what object we're talking about and about what axis, and we can make some conclusions about what the rotation will be like. For example, if I were to race a hoop and a disc down the same ramp released at the same time, because I know based on my chart that the hoop is going to have a moment of inertia of mr squared, whereas the solid disk will have a moment of inertia of 1/2 mr squared. The hoop has a larger rotational inertia and will be harder to rotate, and thus will be getting to the bottom of the ramp after the disk. So this turns out to be independent of the mass. You can think about this as falling objects falling at the same rate or accelerating at the same rate. That's a little bit hand wavy, but it's a good enough explanation for now. Okay, so we discussed the kinematics of rotation. We discussed a little bit about inertia that affects how easy or difficult it is to cause rotation. And in the linear picture, after we discussed that idea of Newton's laws and what causes motion, we also talked about energy. Now, I'm not done talking about the analog to force. I really actually haven't introduced that yet, but I want to take a moment and mention that, like the linear picture, there will be energy associated with rotation. And that's rotational kinetic energy. Something is moving, and so there should be energy of motion associated with that something that's moving. It's just that it happens to be moving in a circle or in a rotating fashion rather than a linear fashion. So we can compute the kinetic energy of rotation by taking the analog to mass. Notice that this rotational inertia is the analog to mass, and this rotational velocity or angular velocity is the analog to linear velocity. So the fact that this is equal to 1/2 I omega squared is again in keeping with this idea that we can draw a straight analogy oftentimes in the rotational picture and utilize equations that end up having the same sort of form. So let's take a look at this person twirling the hula hoops, and let's look at the kinetic energy that's involved here. So we're going to need to know what the moment of inertia is for the hoop. Well, you can see that at various points she is rotating these hula hoops about different centers. This one appears to be rotating sort of at its center, about its center. This one, for example, appears to be rotating about an end point. And so let's approximate that as the moment of inertia for a hoop about the center, and the moment of inertia for a hoop about the end. So for the center in my chart, which you can also find a chart like this in your book, it will just be mr squared. For the rotation about the end, we can apply the parallel axis theorem and say, well, it's going to be the rotation about the center plus md squared according to the parallel axis theorem. So that's going to be mr squared plus what? Plus another mr squared. Okay, so that turns out to be 2mr squared. So this is to say that the moment of inertia will be greater about the end than about the center in this example. And so for the kinetic energy in the center, we've got mr squared, 1/2 of the I, which is this, mr squared times omega squared. The kinetic energy about the end is going to be 1/2 of this I, which is 2mr squared omega squared. So that just equals mr squared omega squared. So no surprise, I have a greater moment of inertia for this axis, so I end up with a greater kinetic energy about that axis as well. Now, kinetic energy of rotation is only one kind of energy that exists. We can also have kinetic energy. Something could be rolling and have translational motion as well, and then we would have 1/2 mv squared. Or it could be at a certain height above the surface of the Earth, and we would have gravitational potential energy associated with it as well. So if I want to know what the overall energy of an object is, I have to consider all the different forms of energy that it has. So in this example, you could ask yourself which of these hoops that is rotating about her body might have the most overall energy or total energy. So although C has a larger rotational kinetic energy, A and B have larger gravitational potential energy. So they're probably going to end up being higher with their overall energy, depending on the difference here in height compared to the difference in the R for the rotation about the end versus the rotation about the middle. Okay, we will continue discussion of rotation in lecture 21.